Hey all, continuing on with our discussion of past climate change, like I said, I wanted to focus on a couple of events, right? Pretty extreme climate events. And digging back through the kind of geologic record back to the beginning of Earth, 4.5 billion years ago, there's really just a couple that stand out that are pretty extreme. The first one that we're going to talk about in this next little segment is snowball Earth. I'm not sure if you've heard of snowball Earth. Maybe some of you had. It's a pretty specific example, essentially, of the way that carbon is moving around Earth, going through some fundamental changes that are really tied to changes on the Earth writ large, like with the biosphere and things like that. So the first thing that we have to talk about when we talk about snowball Earth really is geologic time. That's what I think makes this class cool, right? I'm a geologist. We get to talk about geology things and how they relate to climate. So when we go back in Earth's history, it's long. It's a big chunk of time. And to do that, or at least to organize that and to organize our discussion, we've taken these chunks of geologic time and we've investigated the fossil record, essentially. And when we see changes, we mark them, and that's a boundary of a chunk of geologic time. So we break Earth's history into eons, eras, periods, and epochs. Potentially you've learned about the geologic time scale. But what we're talking about now is really kind of the oldest chunk of geologic time, the time that's kind of an unofficial unit of time that we call the Precambrian. And the reason why we call this the Precambrian, at least by the British who were kind of coming up with the system 150 years ago, call it the Precambrian, is that the Cambrian period, we start to see this explosion of life. Then the rocks are chock full of fossils. Everything below that we call Precambrian. We don't really do that anymore. Well, we do. It's unofficial. We take that chunk of time prior to that. We now know that it's about 90% of Earth's history. And we subdivide that so that we can talk about it. So the last chunk of that time prior to the Cambrian is something that we call the Proterozoic. And what I mean by Proterozoic time, or at least if you kind of think about the word architecture, proto is before, zoic is life. We now know life existed actually before the Proterozoic. We didn't know that when this was all being organized. And the Proterozoic unit of time is also further subdivided into the kind of early, middle, and late, where you hear about the Mesoproterozoic, which is the middle Proterozoic. So actually, you're going to be doing a reading this week, and you'll run into these words, kind of derived from Proterozoic. I just want you to know what those mean and put those in context. Well, let's skip a lot of the gory details, because like I said, this is 2 lectures in a historical geology class, but here we're just kind of investigating an event, right? And so at Proterozoic time, there was, at least in the kind of later phases, there was a landmass, a continental landmass that came together about 1 billion years ago. 1 giga-year, right? That's times 10 to the 9th. So about 1 billion years ago, the continents come together to form this large landmass that we would recognize as a supercontinent. But this one's not Pangaea. Pangaea is way later. Pangaea is like 250 million years ago. This one had a different name, and this has happened a bunch of times. This one is called Rodinia. And Rodinia is going to be where our story starts. So when these continents have come together to form Rodinia, first of all, they form this fairly large landmass that's generally centered on the equator. And one of the things that we have maybe discussed, or hopefully is fairly intuitive, is when you have a large landmass, and this is true even today in places like Asia, the central portion of that landmass tends to not get very much precipitation, because most water is supplied from evaporation from the surface of the ocean. And as that air that's got moisture in it kind of travels over the land, it starts dropping its water. And the farther inland it travels, the drier and drier it gets. Like you could think about the Tibetan Plateau and the Gobi Desert as a good example. So we've never seen anything the size of Rodinia, right? We just have a couple of pretty big continents. And so in the case of Rodinia, it was actually pretty arid. And so that's kind of where we can start, right? You can see here, this is it's kind of more of a diagram showing different continental bits and pieces that came together to form Rodinia. But you can see it's a large continent and it's desolate, right? There's no land plants, nothing like that exists yet. It's just barren rock. That's kind of part of the story that we're going to be investigating. And so Rodinia forms at about 1 billion years ago, and about 750 million 750 mega onium. So, a few 100 million years later, Rodinia begins to break apart through the process of rifting, which means the continent is literally being torn apart. And again, this has to do with mantle dynamics, which, take a geology class, I keep saying. But anyways, so when this starts to happen, that's when things get pretty crazy. The main event of our story here is going to be carbon, right? Or at least going to talk about what happened to carbon. And if we think about what's going on Earth at this time, well, biologically, we know that life showed up about 3.8, potentially a little bit more, but our kind of most definitive chemical evidence is at 3.8 billion years. Didn't really do much, right? It's kind of single-celled organisms, mucking around. Eventually, some of these single-cell organisms evolved to be able to use energy from the sun to create a chemical reaction that sustains themselves. We call that photosynthesis. So remember that in photosynthesis, an organism will consume CO2, consume H2O, and use sunlight as energy to build organic molecules and essentially release free oxygen, right? That's the whole kind of thing of photosynthesis. We work differently. Respiration, which is our process, we consume oxygen and release CO2. So all animals participate in respiration. Most plants participate in photosynthesis. Again, biology students probably throwing stuff at the board. But that's this kind of big, beautiful dance. And I actually referenced this in an earlier video. If you think so, in the modern world, today, the world in which we live in, the world that's been fairly stable for, let's say, the last 500 million years, we kind of have this big, what we call the fast carbon cycle. And this is carbon that exchanges, different kind of reservoirs on Earth fairly quickly, and by quickly, like on the order of years, right? Or even tens of years, or in some cases, weeks. We have plants that are consuming CO2. We have animals that are producing CO2. And generally, those two cancel one another out, right? At this kind of the big picture. But there's a lot of CO2 exchanged in what we call the fast carbon cycle. We're going to have a video about kind of picking apart the carbon cycle in general. There's also something that we call the slow carbon cycle. Well, these two things don't operate in a vacuum, but we could just kind of arm wave at this. Like I said, there's a whole long discussion about this, but we've got sources of CO2 that are long-term, kind of slow, constant sources, like volcanic activity. And we have slow, long-term CO2 sinks, or things that are consuming CO2. Generally, that's rock weathering, so chemical weathering of rock. Rainwater will fall down, it will mix with CO2 in the atmosphere, creating what we call carbonic acid. That will meet a rock at the surface, will cause a chemical reaction, and cause weathering, and that can end up going down the stream and getting deposited into kind of chunks of rocks that we call carbonates, right? So this is really fairly slow, although the rates can be dependent. But anyway, The reason I wanted to describe this is that we've got fast carbon and slow carbon. That's going to become really important later. It's also kind of important for our story because in our story of Snowball Earth, we're introducing the fast carbon cycle.